Oh, I think it is just the same as yours. I don't like this. Is this one? Yeah. I don't eat chicken often. It's like a light one, but not like this. It has like a really color. Yeah. Yeah, kind of.
All right, can we get ready to go? Let's open up the page. Bless you. Bless you. 195. Thank you, Caitlin. That was delicious. So in this last and final section, this is it. This is the grand finale. Okay, this is it. In this last section, we're going to take a look at polar area. So we've been dealing with polar equations and graphs. Now we're going to try to figure out the area underneath some of these polar equations. And what's a little bit different with this compared to the area under curves like we did in Calc 1 and kind of the beginning of this year, when you're looking at polar area, it's enclosed within a graph. Okay, it's not necessarily underneath it. Okay, there's a difference between the two. Because whenever we talked about how we graph polar functions, remember how we always, you can imagine standing at the pole and then you rotate some angle, which is like where you're facing at that point, and then you walk out some distance. So what I want you to think about, and usually I use a clock as a good example, if you were to start the second hand in one location and then stop the second hand in another location, you're trying to figure out the area. I know this looks weird, but you're trying to figure out the area that it enclosed within that time difference. Okay, so think about a clock, like as that travels. So what we're looking at is between this angle theta that we rotated and this angle theta that we rotated, what is the area enclosed between those two angle rotations and that polar curve that we graphed. So it's not measuring to an axis like we did in Calc 1. It's the area enclosed between two angles of rotation. Do we see the difference between the two? Okay, so the formula for polar area is a little bit different because we're not looking at area under a curve, we're looking at an area enclosed in a curve. And we're specifically going to look at the area formula for a sector, because that's the idea of having one starting point, one ending point, and then enclosing it in between those beginning and ending points. A sector you can think about as kind of like a piece of pizza. If you were trying to find the area of a slice of pizza, that is what's called a sector. And that's kind of what's happening here, because this kind of looks like a sector. So the area formula for a sector is 1/2 theta times that radius squared. So just like we integrate the area of a rectangle or a trapezoid to help us figure out area under a curve, we're going to integrate the area of a sector to help us figure out the area enclosed between a polar graph or curve. So theta, we're going to use the d theta on the end because we want to let that angle of rotation get really, really small. Like we'll kind of slice it into very small sections and then add them all up. Remember last year we noticed how the more rectangles we used and the more trapezoids we used, the more accurate our approximation was? Okay, so what we're doing here is we're trying to figure out the smaller the angle of rotation we use all the way through, that would give us a more accurate overall area. So in the end, we're going to have 1/2 times the integral from a to b, or alpha to beta, because we're talking about angles in this case, and we just need the radius squared. But we know from polar equations that the radius is just representing that function they give us, r equals something. Okay, so this section we're just going to practice finding the area enclosed between a polar graph. Some of them are going to be pretty easy, other ones might be a little bit more, I don't want to say difficult, but involved. So we're going to try to decipher between the two and just get comfortable with them. So let's take a look at the first one. Find the area bounded by the graph r equals 2 plus 2 sine theta. Can we graph this? If we can't remember what the graph looks like off the top of our head, that's okay.
Is this the one that's like the upside down curve?
It's a heart, yep. So 2 plus 2 is 4. We'd be up 4 units on the y-axis. 2 minus 2 is 0. So we're at the pole, and we're going to have that upside down heart. So we're basically figuring out the area enclosed between this entire heart shape. So if you were to color it in, we're trying to figure out all of that area. All right. What else is different with this polar area compared to area under a curve? Remember how when we did rectangles and trapezoids in area, sometimes the area could be negative, meaning you were underneath the x-axis? Okay. Polar area should never be negative. It doesn't matter that these are underneath the x-axis. We're just trying to figure out the overall area. So that's another slight difference between the two. Okay, so we first kind of got to figure out, let's maybe set this up. We need the area equals 1/2. We need the integral. We'll talk about the bounds in a second. But then we need the radius squared. They give us the radius equation. And then d theta on the end. Okay, so let's try to figure out what the bounds might be. We got to figure out kind of the starting angle that we have and then the ending angle that we have in order to create this entire shape. So maybe we'll utilize our calculator for that, and perhaps we'll see how we can figure that out algebraically in a second. Okay, so let's go ahead and make sure we're in polar mode, and we'll type in 2 plus 2 sine theta. Before we hit graph, let's go to our window. Let's start with a low theta value of 0, and maybe we'll change the theta max to pi, 3.14. And maybe I'll change my window to -5, +5 in every direction. Did we get the entire heart-shaped graph that we know we should have? No. So if we go back to window, we have to rotate a little bit more than pi radians to get that full complete shape. Maybe we'll try 2 pi. And that gave it to us, right? You see how we started right there and we went all the way through and we ended right there. So we had to go from a 0 radian to a 2 pi radian. That will be our bound. Okay, so let's go ahead and we're going to use our calculator for all of these. Okay, we're just going to type it in and see what we get as that area. What did we get? we go, 18.85. Was that it? Okay. There's our polar area. So far, so good? We just got to make sure we're familiar with this setup. Okay, 1/2, and then we'll use our bounds as the angle measurements, and then r squared. What if, okay, we're going to get there eventually, but what if we wanted to calculate the area kind of between two polar curves? If you think about how we did that for the area between two curves measured to the x-axis or y-axis, this is kind of very similar. Can we think about how we did the area between two curves like last year in Calc 1? For instance, if I wanted to find this area. Mm-hmm. From the top one, yeah. So we had to take the top function's area minus the bottom function's area, because the top function is technically all of this area to the x-axis, and if we subtract the bottom function, which is which is just this section, we'd be left with the area between them. So this is going to act very similarly. We got to take kind of the area from the outer radius minus the area from the inner radius. So it's not necessarily top and bottom like it was last year because we were measuring to an axis. Now we're going to do outer and inner because it's kind of all in relation to that pole where we start our kind of polar journey. Okay, but we'll get there eventually with some examples. But you can think about it as working the same way. All right, let's try the next one. Find the area of one petal, 2 times sine of 3 theta. Can we think about what this might look like? If not, we'll go ahead and graph it. They're talking about petals, so we know this is going to be a flower type shape. Do we know how many petals we should have and how long they are or where they're located? Okay, length 2, and you only double it if it was an even amount. A little different, so there's just 3, okay? And since this is sine, we saw that the cosine petals always landed on an axis. So the sine petals are not going to land on an axis, they're going to be in quadrants somewhere. So at least we know the general shape, but if you did want to graph it, it would look something like this. Okay, so we have the top 2 landing in the quadrants, and then the bottom one's landing on that y-axis because it's for sine. So we just want to find the area of one petal. Maybe we'll shade that in. Now this might take us some time to kind of guess and check on our calculator what our bounds might be, because sometimes it's not always going to be as simple as just pi or 2 pi or pi over 2, something like that. So we might actually have to calculate the bounds ourselves. Maybe we'll just go ahead now and write the general setup. We need 1/2 times the radius squared. But we only want to figure out the bounds that would draw just one of these petals. Now it doesn't matter which petal you pick, but notice how when you draw a petal, it starts at the origin and then ends at the origin, aka that pole. What is your radius if you're located at the pole? Can we think about it? How far did you walk out if you're at the pole? Okay, so that's the length of the petal. At this radian value, we walked out 2, right? That would be a distance of 2. But if you're standing at the pole, how far did you walk out? 0, right? Because you didn't walk out. If you're standing at the pole, you're just, you have that radius of 0. So if this flower petal starts at the pole, and then you walk out some distances, 2 at the max, and then you end at the pole, let's try to figure out where the radius was 0, where you started your journey and then you ended your journey. So we're going to go ahead and set r equal to 0. We're trying to figure out when we're located at the pole. What angle measurements of rotation do we need to just still be standing at the pole? All right, so we're going to have to do a little solving here. We can divide the 2, which would still be 0. All right, unit circle time. When does sine have a value of 0? Think about our unit circle. Okay, so 0, good, pi, and then 2 pi. And then if we divide that 3, we'll have 0, pi over 3, and then 2 pi over 3. We could keep going. Like we could say it's 0 again at 3 pi, it's 0 again at 4 pi. It depends on how many rotations you want to do on that unit circle. But in relation to this picture, okay, at angle 0, meaning we're looking to the right, we're standing at the pole. Any radian value between 0 and pi over 3, we're walking out some distance, which is forming that petal. And then the moment our angle of rotation is pi over 3, we're back at the pole. So we're going to use 0 and pi over 3 as the bounds. Those are the angles that we had to rotate to begin at the pole and then end at the pole. Very similarly, pi over 3 to 2 pi over 3 would probably be the bounds for that second petal. Okay, but they're just asking for 1. So we're going to go ahead and use our calculator, and we'll let that figure out the area for us. Do we get 1.047? Yeah? All right. Let's try the next one. Find the area of one petal. Very similar question. This time we just have a different function. So if we were to think about what this one might look like, we would have 4 petals. We're going to double that 2 of length 4. And since it's cosine, they're all going to land on that quadrant or on the axes. You could use your calculator to graph it just in case you weren't sure. And we just got to figure out the area of one of those petals. I don't know which one we want to figure out. I'm just going to go ahead and shade one in. Okay? But just like, or very similar to the previous question, the area of one petal, we got to figure out where we're beginning at the pole and where we end at the pole. Every other value between those radians is some distance we're walking out to form the petal. So if we're beginning and ending at the pole, we got to figure out when that radius is 0. All right, so unit circle, when does cosine have a value of 0? Can we think about it? Yeah. There we go. We could keep going. The next one would be 5 pi over 2. The next one would be 7 pi over 2 if we wanted to do more rotations. But I think that should be good. And then we got to divide those by 2 to get our angle or theta measurements. So that would be pi over 4 and 3 pi over 4. So all we really do or need to do is figure out two values because we just need a lower bound and an upper bound. So that should work for us. We need 1/2 times the integral. We'll do pi over 4 to 3 pi over 4. And then we need the radius squared. Did we get it? $6.283. Sound about right? Okay. If you wanted to, we could check our work. Let's go back to the top one. If you wanted to, let's go ahead and graph this one again. We'll type in 2 sine of 3 theta. And before we hit graph, let's go to the window button. And let's only graph the window using the lower bound and upper bound that we found. So we'll do 0 for the min and then pi over 3 for that maximum theta. If we hit graph, it should only graph one petal because that's the lower bound and upper bound for just one petal. Looks like it did, right? Because we said there should be 3. If we check the other one, let's see, that was 4 cosine of 2 theta. For this one, the lower bound was pi over 4, and the upper bound was 3 pi over 4. It should only graph one petal. And it looks like it did. Maybe the bottom one, not the right one that I highlighted, but at least we're figuring out the area of that lower petal. We doing okay so far? All right, let's try another one. Find the area inside one loop of that radius equation. Let's go ahead and graph it. This one's a little different than the other ones we did, so we'll definitely utilize our calculator for this one. The problem is, on your calculator, it has to say r equals, so we might have to rearrange the equation. We'll have to take the square root of both sides, so we're going to need that plus or minus. So on our calculator, we actually have two equations to type in. We need the positive square root and then the negative square root. Oh, might have to change our window. Let's do 0 to 2 pi just to see what it looks like. So it kind of looks like a little bow tie. All right, so we want to figure out the area of one loop. I don't care which one it is, but notice how the loop, no matter which one you draw, you start at the pole and then you end at that pole. So let's go ahead and figure out the radius when we have that radius of 0. So so if we plug in 0 for r, we're just left with 4 cosine of 2 theta, and we got to solve for theta. So when does cosine have a value of 0? I think we said that was pi over 2 and 3 pi over 2. And then dividing those by 2, we'll get pi over 4 and 3 pi over 4. All right, so for our area equation, we need 1/2 times the integral with those theta values. And then we need the radius squared. But notice how the equation they gave us, this is already the radius that is squared. So all we need to write is 4 cosine of 2 theta. Do we see that connection, that substitution? All right, so let's go ahead and type it in. We'll see what we get. What'd you get? -2, right? But the area of a polar graph can't be negative, so what do you think the area actually is? Just 2, right. The negative, I think, is referencing either the left-handed pedal, because we're on the left-hand side, or it could be the under area of both of them adding together, because we have some symmetry going on. So don't worry that it's negative, okay? It's just going to be the numbered value itself. We doing okay? Okay, we'll try some more out tomorrow. We'll get into how we can figure out the area between polar curves. That's where it's going to get a little bit different, but so far I think we're doing really good.